Okay, so good evening, everyone. How are you guys doing? I just heard one good. So, is it because you have other classes before this? No. Okay, I mean I'm sure you have, but some of you have. But okay, so we have a midterm next week, so nobody's feeling good. Exactly. It's next week, right? So why do you have to worry about it now, right? Okay. Anyway, yeah, as he was pointing out, there's an exam next week for this class. It'll be in class in this room. Hopefully, it's comfortable. The desk. So I think it's about 2 hours maybe, the exam, and we'll discuss a little bit more about the exam once I cover today's topics. Couple of topics today. The second point is assignment 3 is out, but it's due I think in 3 weeks. So after the exam, you have time to work on assignment 3. Was everybody able to submit assignment 2 on time? Any difficulty with the assignment?
We submitted it on time, but still receiving notification that
yeah, I got the same thing.
Did everybody get such an email?
Assignment is due or past due, and then it
that's why I checked it on Blackboard, and then I saw that I submitted it on time.
Okay. Okay, so it shows the time on when you submitted, right? So as long as it's fine. Don't worry about it. Okay. Actually, assignment 1 grades were out, right? So did everybody get their grades? Did somebody not miss their grades? I know somebody had, but we corrected it. Okay. How are you finding the assignment? I mean, it's going to be, as I said, as well as in these slides, as well as learning goal slides, the assignments are quite complementary. So you will find it as a different realm where you're just doing practical stuff, importing packages, calling functions and plotting things and so on. Whereas here, it's basically, as I said, if you want to ask why I'm taking this course in a nutshell, it's like, why am I doing this? Okay, why am I doing each step in my process? You wouldn't say it's not immediately practically useful because, for example, you could always learn 10 packages per lab, per lecture, and figure out, how to use those 10 packages every week. But then that's partial knowledge, right? I mean, you want to understand, few packages, maybe 5 packages through the course, but really understand them really well. Okay, so basically the why of every step is what we're trying to emphasize, and you want to kind of reason about every step. Okay. Okay, so just to kind of put more context about this, people have taken 572 versus what's happening here is this overlap where, of course, you're gonna work with R and some assignments in R. That's in the center part, right? You will get your hands on experience using some data sets, simple data sets actually. But that's just to understand that, yeah, you're getting the right coefficients maybe, or you're catching the right trends. Maybe things that you see in scatterplot are being reflected in the coefficients that you get from fitting a model, right? But from 572 is again more emphasis. There's a lot more emphasis on a variety of methods. You probably were seeing them for the first time, so they went through it pretty quickly maybe. So here the goal is to go a little bit slow, and that's why we've spent quite a bit of time on linear models. And we also introduced a few other things which you might not have seen: maximum likelihood estimation, some nuances of cross-validation that we'll see today. That's so that you can understand once you change your modeling setup a little bit, and we'll see an example today. So you have to think through what is the assumptions you're making, and is the model appropriate for my data? Okay, so that's always the question, right? Why should I apply a linear model? Should I apply logistic regression? Should I apply QDA? Should I apply random forest? Should I just go with neural networks? It's not clear. So you want to kind of disambiguate that a little bit. That's we'll see an example today in that respect. Okay. So what's the goal for today? In addition to a few review points that I'll try to cover from the first first 5 lectures and including today's lecture. The first point is to kind of just revisit cross-validation a little bit, just to kind of understand when it may fail. So somebody had some questions about when we introduce cross-validation, how many folds, how big the data should be, can I work with 10 examples or can I work with a million examples, right? So we'll see a couple of examples when cross-validation makes sense. The second point is maximum likelihood estimation as a unifying view for several of the techniques that we saw in the first few lectures, both classification and regression. But the interesting thing is some techniques don't lend themselves to maximum likelihood estimation point of view. Okay, for example, support vector machines doesn't lend itself to maximizing some sort of a likelihood, some sort of a probability distribution. Okay, that's what the likelihood is, right? Last time we worked through an example of maximum likelihood estimation, which was just estimating the mean of a normally one-dimensional normal distribution, right? But today we'll see another example if you have time, which is something called a naive-Bayes classifier. This is something I'm just giving you an example of in today's lecture. Okay. A third point is going to be about Bootstrap. It's actually at the first level, it's going to be pretty simple. There is a lot more that goes into understanding Bootstrap when it's not applicable and applicable. But today we'll try to understand the extreme basics of Bootstrap. Okay. And that's it, and then the review. So these are the 4 goals for today. And any questions about where we are, where we're headed? Is the larger picture clear? So we have covered this basket of linear methods so far for supervised learning. But there's the whole world of machine learning doesn't just involve linear methods, doesn't just involve supervised learning. It involves things like unsupervised learning that we'll see later on in the next the last part of this class. It will also involve time series methods, which we'll also see in this class. It also involves things like causal inference, which we'll not see in this class. Okay, and it involves many other nonlinear methods like neural networks, which are topics that we'll kind of skip in today's in this lecture, in this class. But there are some elective courses like I teach 576, which is advanced prediction models. So there we kind of spend most of the time on again supervised learning and unsupervised learning, but a complementary set of methods useful for a different type of data, for a different class of data sets, which are mostly, people call it unstructured. They're not tabular. Think of images and text and so on. Okay. That reminds me, how was the handling with the zip code data? Did you guys have any difficulty with working with zip code data for your assignment? So did anybody plot any observation in that data set? Were you able to plot and see an actual digit? You should try, I mean, since you already loaded the data and you have that file, or maybe in your RStudio environments, you should pick an observation and just reformat that 256 dimensional vector to 16 cross 16 and just draw what is called a heat map, for example, and you'll get to see what the digit is in the image. Okay. So let's see. So last part is before I get into cross-validation examples. This is the link on the 6th lecture notes. Okay. So this is just to get you interested in, I guess, this is a demo of a 3-class classification problem, I think, which I'm not going to show because I've hooked up my webcam in a different way. So you guys should try it. You can actually generate training data for 3 classes online. You just need a webcam and you can create 3 classes and actually see in real time how classification happens, how a model is trained in the browser, and then it's mapped to some decision. For example, I think they show some GIFs of cats, probably, something like that. So this link is there on the lecture notes, so try it out during the break. Okay. So okay, so last time I was, towards the end, I was trying to talk about model selection and model assessment. Okay, so just to recap, and I think I went over this a little bit quickly, there are several methods to assess models. Assess models means you already have, let's say you just did linear regression, no ridge regression or subset selection or anything like that, which means that given your training data, you had this nice closed form expression, right? So beta had, or you could also solve using gradient descent. You had this expression which was X data matrix transpose X data matrix, inverse X data matrix transpose Y vector. Let's say it's one-dimensional output. Then you build this model. Then you want to assess this model. How does it perform in the future? Okay, so there are different ways to assess a model. Okay, one way is to actually use the same ideas from cross validation, which is that when you construct similar ideas from cross validation. So if you had lots of data, then you really don't need so you don't really need a cross validation type of a setup. So here, if you had lots of data, you could just break your data into two parts, keep a part of the data aside, and just evaluate your model on that data set. Okay, hoping that for example, if your full data set is let's call it X. So this is the X, and then X, let me call it test because I'm really not going to use it. Break it into two parts. Maybe this is has D columns. Okay. You just break your data set into two parts if you have lots of data, and then just build a model using the first part of the data and assess the model using the second part of the data. That's a valid approach, but you should have lots of data, and hopefully the data is similar across the two parts. In the sense, for example, if you collected sales data across time, maybe the sales characteristics at the later part of the time is different from the sales characteristics at the beginning part, then it's not going to be it's not going to evaluate your model well. Okay, that's but that's generally this is generally called model assessment, where you already have a model, okay, and you want to figure out how well it's going to perform. Okay, and the second thing was selection, and this is where I said you have a collection of models or a collection of model families, for example, linear models versus support vector machines or something like that, and you want to figure out which model family to select. Okay, you're not right now trying to tie yourself to a particular model parameter itself. For example, you may want to pick linear models, but you're not tied to any particular linear model vector in there. Okay, no particular beta hat. So you want to pick linear models versus support vector machines. You want to figure out which model class is good. Okay, for that, what we said is you can actually do cross validation, which is a choice. So every time you have a choice, whether it's across models or within a model family, things like what should be the k for k and b, or what should be the lambda coefficient for a ridge regression model B, then you have a choice, and you can pick those choices based on cross validation. So when you're picking the choice, you're not really caring about the particular model that you got along with it, because in cross validation, let's say you have three folds, right? I have tilted the data, but if I have fold 1, 2, and 3, then if I use the first two folds to get a model, let's call it beta 1 2, beta hat 1 2. I don't really care about that particular model. I just want to know how well this model for a particular choice, maybe lambda is equal to 10 to the power minus 2. Let's say I'm doing ridge regression. Okay, for a particular choice, I have a model. I just want to know how well it performs on the third fold, the fold that I did not use in my training data, and maybe there is some performance. Okay, performance on the third fold. Okay, so that performance number is what I care about for the fixed choice that I took, fixed choice that I made. And then I flip the folds, maybe use fold 2 and 3, get another model, beta hat 2 3. But I don't care about that particular model itself. I care about the performance of that model on the held out fold. Okay, and I can get performance 3, performance and performance 1, 3 different numbers, and I can average them, and that's going to be my performance of a model from this family, let's say ridge regression family, when the lambda is 10 to the power minus 2. Okay, So that's the number I care about. If my lambda was this, then what would be a good performance for this model class? Okay, and that's the idea of selection. Okay, so that's the slight difference between selection and assessment. Any questions about selection and assessment? I illustrated that using just cross validation, but there are many techniques, and last time I drew 2 buckets or 2 sets. Okay, so the first set was cross validation and I think Bootstrap. Okay, so these are ways to do model selection as an estimate, I guess ERR, or basically the generalization error. Okay, estimate this generalization error or test error, expected test error. It's all the same thing. Estimate ERR directly. And there was the other set where I wrote a bunch of acronyms, basically AIC, Bayesian Information Criterion, minimum description length, and structural risk minimization. Doesn't matter. Let's not worry about these acronyms. I'm just putting few techniques there, which what they do is they don't estimate this generalization error directly. What they do is use training data, or use training error. Okay, let's call it training error. They use training error and then they add a bonus. When I say bonus, just think of it as an additional term. So they don't think in terms of cross validation or anything. If you have a linear model, fit a linear model, okay, there will be some training error that it gets. Okay, then you just add a term, add a number to it, to the loss, the training error loss plus that number is your estimate for EPE for that model. Okay, for that model class. Okay, so if you fit a linear model for lambda is equal to 10 to the power minus 2, let's say same thing, lambda is equal to 10 to the power minus 2, you fit a linear model, you got a beta hat. Okay, using all your training data, no folds here. You got the beta hat. There will be particular training error for that model, right? You can just get it from the function that you called, or something like that. And then the training error plus an additive term is going to be your estimate for how good this particular model is. Okay, which means that it's an estimate for your generalization error, and you can do this for different models, different types of models. Okay, maybe for lambda is equal to 10 to the power minus 4, or 10 to the power minus 1, or even 1. You can have different models. They'll all have different training errors. You can add these offsets to the training error and see what the performance difference is. Okay, it turns out that for range regression, I'm not sure if there is a big difference, but for example, BIC, I think the additive error is additive term. This bonus term is I think something like d log n by n, where n is the number of observations, d is the dimensionality of your model. So for example, if you're comparing 2 models, let's say you have tabular data, 20 features. Okay, now you're comparing 2 models. One model works with 10 features, the other model works with all 20 features. Then the d is going to be 10 or 20 there. N is going to be the same as before. Okay, so it's just a way to offset. So when d is lower, then you are adding a lower bonus. Okay, so ultimately you'll choose that model which has the lowest BIC or AIC. So for example, the training error for a 10 feature model may be high, but this bonus term is low because d is low, and the 20 feature model may have training error low, but the d number would be high. So you'll compare and contrast between them. Okay, but these are a little bit more traditional, and there's a lot of assumptions that goes into it. So that's why I am kind of not in favor of them. I prefer people use cross validation. Yeah, what's your question?
Can you explain again about the bonus? Is it a scalar?
Yeah, it is just it's a number. So training error is a number. Let's say it's normalized. So training error of 20%. Okay, plus a bonus. The bonus is going to be something like this. Okay, this number. So if you know n, if you have 100 observations, log n divided by n times d, for example. D is for linear models. It's kind of clear if you are using different size models, but there are different ways to estimate these essentially degrees of freedom. Okay, but yeah, but there are a lot of details there which I'm skipping over. Okay, so today we'll see Bootstrap and cross-validation. Cross-validation we've already seen before, but I wanted to take two examples from the examples as in very illustrative examples to talk about what are the issues, what could be some issues that you may face with cross-validation. Okay, so if you have lots of data, so let's say you have a million rows and you have two features, okay, you don't need cross-validation, okay, because for two features you can literally plot, scatter plot, are essentially, you know, two features plus one dimension for prediction is essentially three-dimensional data. You can actually visualize what would be the pattern in the data. Okay, and if you have lots and lots of data for this two-dimensional problem, then you can just put, you know, subsample some observations and just put them aside as your validation, one single validation or test set, and just learn a model on one of the you know, the other remaining data, and evaluate, assess its quality on the held out data set. Okay, so that's it. You don't really need cross validation. So for really large data sets and really small features, then you don't really need cross validation. So what happens when you have small, you know, less amount of data? Okay, so in the notes in example 9, but example 9 talks about this type of an issue. So what is it about? So let's say there is a, you know, you're fixing your model family, let's say linear model family, and on the x-axis I'm gonna draw n. So what is n? N is the number of observations that I have in my training data. So it's as if I had a million observations, but I'm only revealing to you maybe 10% of it, maybe not even 10%. Let's say since it's n, it's like, okay, 100 observations, 200 observations, 300 observations, all the way to million observations. If I reveal that much information to you, you can build a model for each amount of information that you are exposed to, right? So on the y-axis is 1 minus error. Okay, this, just think of this as the actual generalization error. So we don't have access to this, we can't compute this directly. So if error is low, then we are closer to the number 1, right? So let's say it's so this is 1 over here, okay, and this is 0. So typically, and this is called a learning curve. You will see that the learning curve increases something like this. Okay, it may not go all the way to 1, so let me just redraw it properly. Okay, so a learning curve looks like this. This is an idealized illustration, but if you have lots and lots of data, and hopefully the model is good model class for this, maybe in reality the conditional expectation of y given x is linear, for example, then this is how your learning curve would look like. So as you have less and less data, then the model that you learn will not have good performance, okay, as a function of data set size. Now let's say so let's say this number here is 100. Okay, so beyond so 100 is this number of observations before which it looks like the you know, the accuracy 1 minus error is varying, is highly sensitive. It's varying all the way from, let's say, 0 to almost to 1, or 20% to 80% in that first 100 observations, and then beyond that 100 observations, adding more data is not really increasing my accuracy too much. Okay, then if you use k-fold cross validation to learn a model, now we are specifying a specific model, okay, where k is equal to 5, and let's say I have 200 observations, okay, then in each fold I have about 40 observations, right? Okay, so if you look at this, if you okay. So each fold has 40 observations. I use 4 of the folds. I mean, I said 5 folds is equal to 5. I use 4 of the folds to estimate a model, and then I use the remaining fold to learn how well the model is, right? Which means that 4 times 40 is 160 observations is what I use to train my model, right? In this setup. Then if I use 160 observations to get, let's say, a beta, let's say I'm using linear models, then can imagine the performance will be somewhere over here. Okay. The performance that I can estimate of that model, okay, because I use 160 observations, I'm gonna look at the x-axis around 160, and I'm gonna I mean, this is the idealized curve. If my held out data set, which is of 40 observations, may give me a number which is around that. Okay, but if I use if I had only, so this was for 200 case. So what if I had only 50 observations? Okay, 50 observations. If I had 50 observations, then I have, if I do 5-fold cross validation, I have 40 observations in my 4 folds and 10 observations to evaluate how well the model is. Then 40 observations would give me a model which would have an accuracy which is over there. Okay, so even though the model family is the same, if you have lesser observations, you may be switching between a region where you're able to estimate the accuracy as, let's say, they're over 90%, versus a smaller data regime where you're estimating the accuracy as 50%. It's the same model family. Okay, it's just a choice of, I mean, even the k-fold k is fixed. There's just the number of data has changed from 50 observations to 200 observations, and because you're using different size data sets, in one case, the second case 40, and in the first case 160, you're getting different models. Okay, and the models perform very differently. Okay, as the size of the data changes. Okay, so in the second case, you are vastly underestimating the accuracy of this model class. Okay, so for small data set, you may be underestimating the performance of even linear models, for example. So this is just a consideration of, I mean, this is something that you would not know when you're in practice. You have, let's say, 20 features and 2,000 observations. It's not clear which regime you're in. So you can always try, 5-fold, 3-fold, and see if it is sensitive to the numbers that you're getting. Okay, this is just a very empirical, I guess, heuristic way of doing things. But you can see whether the fold choice has an influence on the accuracy numbers that you're reporting on the validation, as in the accuracy numbers you're reporting. Okay, is that fine? Any questions? Yeah. So next, let's look at another example, and this is a example where the goal or the moral of the story is going to be that whatever choices you make should be inside the cross validation loop. Okay, as much as possible. So what do I mean by that? Okay, let me repeat what I said. Whatever choices you make in your data analysis process to get to the model, try to push many of those choices within your cross validation loop. By which I mean, for every choice of model, like the lambda for ridge regression or the k for KNN and so on, for every choice, let's say you have k-fold, maybe k is 5 again, then so you pick 4 folds, right? You pick 4 folds and build a model. You can pick those 4 folds and do okay, let me just pick 4 folds, do a scatter plot. Okay, if you want. I mean, so if you're anyway doing scatter plot, so this is where I'm saying that if you're doing, so let me report the incorrect way of doing things. You could always scatter plot your features with outputs. Okay, let's say we are doing regression, so you can just look at features versus outputs for each feature, Maybe some look correlated, some may not. Okay, so you looked at the scatter plots. Okay, maybe there are 20 scatter plots because there are 20 features. Then you saw that okay, some of them doesn't seem correlated, very noisy, so you drop them. Okay, then you got, let's say, 5 or 6 features. Then you use those 6 features and then do cross validation. Okay, to pick maybe the k for KNN or lambda for regression or something like that. Okay, so that would be an incorrect way to do cross validation and to get a estimate of EPE or generalization error. Okay, why is that? Because you use the data to first do feature selection. Okay, and you use the same data again to estimate EPE. Okay, so the same data was used to do some intermediate step, which further was proven to estimate the EPE performance of your model. Okay, because it's the same data source affecting both, the estimate is not going to be correct. Okay, so you should push this scatter plot business into the cross validation loop. Okay, then you will get the right estimate for your model. By which I mean, if your choice, you have some choice for your model, pick 4 folds. Let's say you're doing 5-fold cross validation. Pick 4 folds, and in those 4 folds do scatter plot. Maybe you pick 5 features, whatever, you eyeball things and you pick features, and build a model, get an EPE score. Next, you're changing from those 4 folds to some other 4 folds, right? Again, you do scatter plot. Maybe you will not get the same 5 features. You may get something else. Okay, pick the appropriate features, build a model, get the score, and so on. So that's an example of how to, relatively more correctly do cross validation than before. Okay, that's an example. Is it clear?
So
yeah.
We should not drop the features before. Does it mean that?
I'm just saying that if you're gonna, so in a data processing pipeline, if you drop features based on correlations with the outcome and then do some cross validation or some choice, then the reported numbers are not going to be the performance of the model, will not be the correct performance of the model, because you use the same data for initial pruning or initial selection, which is outside the cross validation loop. Okay, you use the whole data, training data, to do some selection, so do some choice. For example, feature selection in this case, eyeball the features which are correlated, and then again you use the same data to split it into folds and estimate a model based on a subset of these features. Then the estimates will not be correct. Of course, you scatter plot and then forget about whatever inference you got from the scatter plot and just do cross validation. Then it's fine. Okay, there's some nuance there. I'm just saying that you should not use the whole data to make some decision and then do cross validation on that subset of the data, or subsetted data. Okay, that is the issue. And further, the issue only arises if you're looking at input and output relationships from the data. So in the training data, I could ignore the outputs, seal it away for now. Just look at my features. Okay, maybe feature correlations, and drop some features. Okay, that is okay, because that's not informing me anything about predicting a model. Predicting the output. Okay. So you can do feature selection when you're not looking at the outputs, but that's not clear, right? How can you do feature selection when you're not looking at the output? There are ways. I mean, you can look at 2 features estimating the same thing. Maybe they're highly correlated. You can drop something like that. Drop one of them. Okay.
But if you're using our business acumen to do feature selection, then it's fine to do cross validation.
So if you're using, if you're not using data, so if you're using business acumen, you mean prior knowledge, then this is, so it's whatever information you're deriving, as long as it's not from the current data that you have, it's fine.
We're not using the data to tell us what features should be selected, then it's fine.
Yeah. Prior knowledge plus this whole procedure is data driven, right? We don't know which model to pick or which parameter to choose, so then we are using the data to do so, and we're estimating the EPE of the model. It's just the EPE of the generalization errors of the models will be incorrect if you use the same data to do something else before and then feed information to the next part, which is this model building part. That's all. Yeah.
So essentially, if you're going to use cross-validation to select features, you're saying don't use the same parameters for cross-validation to test the accuracy of that?
I'm saying do the feature selection inside the cross validation loop. So let me go through an example which which may give you a better idea about this idea. So this is example 10 in the notes. Okay, so on page 13. So actually, yeah. So in this example, n is equal to 50 and p is P is 5000. So clearly you can see, you can't really do much here because the number of features is 5000 and number of observations is 50. Okay, and in fact all the xi's, there are 55,000 of them, are actually just normally distributed random variables. I guess mean 0 and variance 1, and xi's have nothing to do with the y's. Okay, so y's. So the model actually is 0 times x1 plus 0 times x2 plus 0 times x 5000. Okay, that's the true model. And it's actually it's okay. So the model, okay, there's a variable g which is indicator of whether y is greater than 0, let's say. Okay, by which I just mean they transform that regression problem to a classification problem. Just think of, if y's are positive, then it's a positive class. If y's are negative, it's a negative class. Let's say this is the true data. So you can see that the true prediction error should be 50% because features have nothing to do with the output. Okay, in fact, probably the output is also Gaussian with mean 0 and variance 1. So which means that with 50% chance you will have positive numbers, with 50% chance you have negative numbers. So your error should be 50%. Okay, but if you use so if you do the following, which is 1, okay, you scatter y with xi, you do 50,000 such, sorry, not 50,000, 5,000 such plots. Okay, there are 5,000 variables. Okay, scatter y and xi, pick 100 of them which you think are highly correlated. Okay, I mean you can visualize, right? I mean you can two-dimensional plots, you can visualize, pick 100 of them, and then build a classifier. Okay, and if you get its so when you build a classifier, let's say you're figuring out choice for k is equal to 1. Okay, k nearest neighbor, 1 nearest neighbor. Okay, so k and n, so this k is different from the k fold, so k is equal to 1, so 1 nearest neighbor. Okay, that's the model family. Then if you build a classifier, or for this choice, if you look at its cross validation score, or basically the estimated EPE, it's 3%. Okay, so in reality it should be 50%. Reality or ground truth is 50%, but if you do this, you get 3% as the performance of a 1 nearest neighbor classifier on your data. Okay, so this is an example. This is what I'm talking about. So you did feature selection, which is through this scattering and picking, and then once you pick those 100 features, okay, you're finding out, given those 100 features, I do k and n for maybe different choices. For k is equal to 1, you can estimate an EP, right, generalization error. So that error is going to be 3%. I mean that's what's shown in this plots, figure 11 as well. Okay, so yeah. So and the issue here is that you use the data for both scatter plotting and informing your scatter plots and therefore feature selection, and using the same data for estimating the EP for your model. Okay.
This is a bit tricky concept because we've been taught that data preprocessing comes before your model building
Yes.
exercise, right?
Yes.
And after that, you assess your performance of the model.
Yes.
So what process flow I had in mind was always to look for feature selection and then decide your model,
Yeah.
a particular algorithm, and then do assessment using cross-validation.
Yeah. So you can do feature selection. I'm just saying you should not use the scatter plot with respect to y and xi. So you're saying if you want to do this outside, then then you are already so just think of the alternate scenario, right? If you did this, if you picked these 100 features, maybe not in this example, but in general 100 features, if you got the same 100 features in every 4 folds out of 5 folds, then you're fine, because your answer wouldn't change whether you picked these 100 features before or not. Okay, do you understand? So I'm just saying that if you had put that loop inside the cross-validation loop, put that step inside the cross-validation loop, depending on the folds, you might get different answers. And that's actually I didn't tell here, but that's exactly what's happening here. If you put that scatter plotting business inside the cross-validation loop, for different folds, you would get different 100 features, because first of all, there's no correlation there's Fourier's correlation between those 5,000 variables and the output variable. Okay, so that's basically the catch. Okay, if it's a risk, you can always do something, you can always do something which is incorrect and get away with it basically. But if you're trying to pick across models, if you do feature selection and you're trying to pick across models, I still think this could be erroneous if you do it this way. Okay. But if you're just looking at just the x's, the input variables only, ignore the outputs, and then you're doing some data processing there, things are looking multicollinear, because the scatter plot between xi and xj is the same, is like a 45-degree line, dropping those features, that's fine. Okay. So does this example clarify a little bit more about what's happening? I'm just saying that there are some steps. This is the ideal way to do it, which is if you're using data to inform some part of your model choice, then that data to inform model choice, hopefully everything is inside the cross-validation loop. Everything else can be outside. Okay. So you cannot use the data to inform choice outside the cross-validation loop. Again, use the same data to inform choice again inside the cross-validation loop, and estimate a good, get an estimate for the generalization error. Okay, that's the issue. Yeah, so people, and in fact in the notes, they do it inside the cross-validation loop, and then they show that the error is actually the correlation. So they're looking at, instead of EPE, they're looking at correlation between correlation of selected predictors with outcome is 0, actually mean is 0, whereas if you do it incorrectly, if you pick the 100 features outside, then your correlation is going to be positive. It may look positive, okay, which is not the case in this contrived data set. Yeah. Okay, so any questions on this part? So this is just to think about sizes of data, number of folds, and things like choices that you're making based on the same data. In fact, that also reminds me, somebody was saying, can we interpret the coefficients and the confidence intervals and p-values and so on, right? So that's again the same issue, which is that you had data, you pass it through, you did not do any selection, any data-driven choice beforehand, and just use the data, passed through a linear model and got beta hats and confidence intervals. Maybe then you can interpret the confidence intervals, okay, under some modeling assumptions. But if you use the data to do some filtering or do some operation like feature selection in this case, and then you use the same data to estimate the model coefficients, then the coefficients, what is it called, the confidence intervals are not correct. Okay, this is a glossed over point, but it's the same idea. So you're using the same data to inform two different things, then they interact in a highly nonlinear way. Okay, so thinking about confidence intervals doesn't make sense, and you'll see that we'll look at Bootstrap in a few minutes, is a way to talk about prediction uncertainty or even model uncertainty in a fairly unambiguous way. Okay. Any questions? How many of you are not following what I said in the past few minutes? Which part?
Confidence interval.
No, I'm just saying it's the same thing, right? So what was the issue here? So even if you don't understand the nuances of each step here, the issue is you're using data to do feature selection, and then using the same data to estimate the beta hats for the selected features, right? Maybe out of 5,000 features, selected 100 here, and then I estimated beta hats for the 100. Then the confidence intervals don't make sense because you use the data, same tau. Remember, I had this tau business in the bias-variance trade-off. The same data you use for both selecting the features and then as this next step using the same data to estimate the beta hats of the selected features. Okay, that's different from using the data, maybe using something like what is this? Something like this and getting the confidence intervals. Here you're not doing the first step of feature selection using the same data, right? So then those intervals or hypothesis tests make sense, but in general they don't. Okay. There are also lots of assumptions under which those hypothesis tests make sense. Okay, normality assumptions and so on, which we gloss over. Yeah.
In your example, you had 50 observations, but
yeah.
5,000 variables.
That's just for illustration.
And each of your 4 folds, you only used 100 variables, right? Or,
yeah.
How would you have enough information to make any conclusions about your variables since you're not even using each of them once?
Yeah. I use it's a 5-fold cross-validation in this example, so I used only 40 observations to get my. I mean, in this case, I don't even need. Yeah. So in this case, in KNN you don't really have. You're not building a model as such. So your question is what? The number of observations is quite low. Yeah. And if you're doing 5-fold, then only 10 observations per fold. Yes.
That, but then it was my understanding that in each of the folds you were randomly picking 100 different variables, right? Out of the 5,000.
If you do that, then that's the correct way. If you do that, then you will see that there's supposed to be like zero correlation between inputs and outputs.
But wouldn't you need enough folds so that every variable had an equal chance of being represented? Let's see. So if you only do 4 folds and you pick 100 variables in each, then you'd have a grand total of 400 variables, right? And so most of the 5,000 aren't gonna have a chance to.
So you're picking from 5,000, right? So you do use the 5. Yeah. They will not be featured in your, I guess, model prediction part when you do some prediction on the held out data. But you're using 5,000 to 100 conversion within each fold. That's the right way to do it. I'm saying that if you pre-select 5,000 to 100, then you already know that they're highly correlated. Your cross-validation number is going to be, we'll say the correlation between input and output is 50% or whatever, pretty high. Okay, which is not the case. Do you understand what I'm saying? If you pre-selected, then you are already selecting for highly correlated features. This is just spurious correlations, and then your cross-validation is not even telling you anything. It's just saying that you picked the right, right 100 features. Okay. If you do that selection loop inside cross-validation, then you will see that every time you're picking different ones, and therefore, on average, they wash out. Okay. Is that not clear?
No, that's fine.
So you should do feature selection if you're going to use inputs and outputs inside the cross-validation loop. So ideally, if there is a code, you just put that inside your for loop of cross-validation. That's all. It may pick different features in each 4-fold to 1-fold, process. Yeah.
So the biggest difference and issue here is not that you're not your folds, but the fact that you're selecting your variables based on a scatter plot, not.
And using the same thing. So you're using data to do some initial pre-processing, or it's not like initial pre-processing, this selection of feature selection, and using the same data to again estimate the generalization performance of your model, in this case k nearest neighbor. That's the issue. So you should not use, then the estimated numbers are not going to be correct, is what I'm trying to say in the cross-validation part. That's all. So if you push that feature selection into the cross-validation loop, then the estimated numbers will be fine. Okay, so now let's actually move to another topic, which is, okay, I wanted to, so last time actually I spent some time on maximum likelihood estimation. So I will give another example of maximum likelihood estimation because it's kind of just to show that it is definitely of interest for thinking about new models. So there was some section, there was some at the beginning of the class I showed that you should be able to think about new models. So how many of you have seen naive Bayes classifier? Naive Bayes classifier. It's a simple classifier typically used for, typically is motivated by saying, okay, we can do spam classification. Okay, given an email, we can figure out whether it's spam or not spam. Okay, so I'm gonna tell you how naive Bayes classifiers parameters can be estimated using maximum likelihood estimation. Okay, so this is not there in the notes, but I thought I'll just motivate it as an example. There's some other, there's the usual normal distribution maximum likelihood estimation in the notes, but naive Bayes is very similar. So let's say I have only 3 words in my vocabulary. Okay, so there are only 3 words. Every email consists of only these 3 words, or some subset of them, or repetitions of them, and so on. So let's say word 1, word 2, word 3 these are 3 random variables which tell me whether that word is present in that email or not. Okay, so it's, my vocabulary size is 3. You can think of it like 30,000. It's the same thing, and each W, capital W, just says whether in this generic email whether the word is present or not. Okay, on or off, binary feature. Okay, so naive Bayes model, it's a model of classification where probability of y is equal to spam given features, which is W as something little w1, little w2, little w3. Let's say W vector. This is what we want to this is what we want to find. Okay, if this is greater than probability of y is equal to not spam given W is equal to little w, which is, in this case I'm just saying that P is 3. Okay, that's this thing is W. Okay, let's put transpose here. So if this probability is greater than the second probability, then I classify it as spam, right? This is how you would do classification, right? So there's some theta, just like remember logistic regression, LDA had some theta. Theta just means a bunch of parameters related to the LDA had like 5 parameters, mu1, mu2, pi1, pi2, and some sigma, right? So 5 parameters, and they were all different dimensions. Okay, there were some dimensionality also in there. So in naive Bayes, we assume that the probability of y is equal to little y. Okay, I can use G also. Okay, it's the same thing. Given W is equal to little w is proportional to probability of W is equal to little w given y is equal to little y. Okay, times probability of y is equal to little y. Why is this true? This is just Bayes rule. So if I did not put proportional to, if I had said equal to, then divided by probability of the word. Okay, it's just Bayes rule. So naive Bayes makes this assumption that this conditional probability of words, okay, probability of words given a class is just the product of the probability of words given class. Okay, product of each word given the class. So probability of w1 is equal to little w1 given y is equal to y times probability of w is equal to w2 is equal to little w2 given y is equal to y times probability of w3 is equal to little w3 given y is equal to y. So this is called the naive Bayes assumption. So first step is just Bayes rule. We did not even bring in thetas there, so there is some theta here, but let's not worry about it. First step is Bayes rule. Second step is the naive Bayes assumption, which says that conditioned on the class, the probability of a word appearing, probability of the 3 words appearing. So like this underlined thing here, right? Probability of word 1 appearing, word 2 appearing, word 3 appearing. That's I said these words are binary. The w variables are binary. Is the same as probability of word 1 appearing times the probability of word 2 appearing times the probability of word 3 appearing. Okay. So this is the independence assumption. So condition on spam, whether there's a word, first word coming has nothing to do with the probability of second word appearing. Okay. So that's the assumption. Okay. So now how is this? And then there's also this prior. Okay. Probability of y is equal to spam itself. Now if you do, so is the model clear? So here we have not introduced data at all. We are saying y's and w's are indicator variables for words. There are only 3 words in my vocabulary, and probability of y is equal to spam given words is equal to present, not present is proportional to this product here. Okay. Now here is the model. So what is going to be the theta? We're going to assume, so see, y is binary, so we can just think of that as Bernoulli. Word present or not present is again binary, so we can just think of that as Bernoulli, right? So all my parameters are just going to be what is the bias of this guy, this guy, this guy, in the sense that each of these terms is like little w1 can either be 1 or 0 is what I'm saying. So given the class is equal to, let's say little y is spam, let's say it's spam, okay, little y is spam, then I'm just saying given spam, what is the probability of the first word being there or not? Okay, that's like a Bernoulli. Okay, it's a conditional Bernoulli. Condition on spam, I can compute this number. Similarly, condition on spam, I can compute this number. What is the probability of word 2 appearing? Condition on spam, what is the probability of word 3 appearing? I can compute these numbers, right? And this guy prior is what is the probability that this email is spam or not? Okay, irrespective of what words appeared. Okay, so all these 4 objects, so there are 3 terms here and square this prior thing here. I'm assuming all of them are Bernoulli. Then the maximum likelihood estimate of a Bernoulli gives us the parameters of this naive Bayes model. What do I mean by that? Probability of y is equal to spam is estimated using number of spams divided by n. If I have n observations, the number of spam emails in that is essentially an estimate for my y is equal to spam, okay, because y was Bernoulli, right? And this you can actually get. So why did I get this number? So why did I put squiggly? Because this is an estimate. So this is an estimate. This is like think of it as p hat for this y variable. Okay, but the y variable is an estimate. Okay, or you can just call it theta1, whatever. And how did I get this? Like, why is this number of spam emails divided by n? Is because is potentially a homework. You can just do it by doing maximum likelihood estimation. Okay. So we just said y is Bernoulli. So figure out what the Bernoulli random variable, Bernoulli probability mass function is. Okay. So let me not use. Let's call it theta1. Okay. So theta1 hat. So I'm just saying that you can estimate this by MLE. And why is that? Because we know how a Bernoulli random variable's likelihood function looks like. Okay, which is that. So for example, probability of first observation is equal to spam is theta1 to the let's say y is equal to spam is y is 1. So indicator of y1 is spam times 1 minus theta1, indicator of y1 is not spam. This is just a fancy way to say that if it was spam, then the probability of me observing that is theta1. If it's not spam, probability of me observing that is 1 minus theta1. Okay. Okay. not spam here. Oops. Okay. Whatever observation I got, little y1, whether spam or not spam, this is the likelihood of that observation. Yeah.
So for the MLE, the posterior distribution of the y given the parameters should not necessarily come from Gaussian distribution.
There is no Gaussian distribution. Everything is Bernoulli here.
Yeah, here in the proof that you said that you got the log n, it was possible because it was Gaussian,
Which proof?
for the maximum.
Log n? We did not get log n, right? Oh, we were doing maximum likelihood estimation for a Gaussian distribution last time. So instead of this, so this is called this is the likelihood function, right? The function of θ1. Okay. Now in the Gaussian case, there was 1 by square root 2 pi e to the power minus y minus mean square divided by 2 times variance square, some distribution like this. So yeah, this would be the likelihood of the data if my parameters was mu and sigma. Okay. Here because it's Bernoulli, there's only one parameter theta. Okay. And I wrote it in a product form. It's just a messy notation, but all it's saying is whatever be little y1, whether it's spam or not spam, pick the appropriate term because the other term is going to be 0. Because there's a to the power indicator, right? So one of them is going to be something to the power 0. It's going to vanish. Is it not clear? So anyway, so there's a likelihood function last time that we saw. That was a Gaussian distribution, and we wanted to maximize this type of function over mu and sigma, and this time we want to maximize this type of function over θ1. Okay, and if you take the log, so if you take the log of probability of y1 is equal to y1 plus log of probability of y2 is equal to y2 and so on. How many observations I have? Log of probability of yn is equal to little yn. Okay, so this is my total likelihood, the likelihood of my data. I have n observations. This, if you take the log of a to the power x plus times b to the power y is just indicator of whether y1 is spam times log of θ1 plus 1 minus I guess that, okay, plus indicator of y1 is not spam times log of 1 minus θ1. Okay, and there are n terms, so you just sum over I is equal to 1 to n I. Okay, so this is my likelihood function. Log likelihood function is this. Okay. I just took this term, multiplied it n times and took a log, and that's all. There's a summation over this. So this count is the number of spams, right? And this counts would be number of non-spams. They sum to n. Okay, so you can replace. So if you had this summation, this is the number of spams, and this summation here, I mean with that summation included here, would be n minus number of spams. Okay, and if you maximize over theta, you will see that theta is equal to number of spams divided by n. You just take the first derivative with respect to theta. Log of first derivative of log theta is what? 1 by theta, and then first derivative log of 1 minus theta is again something else, minus 1 by 1 minus theta. So you just set it equal to 0, you'll see that theta is equal to number of spams divided by n. All I'm saying is, you may see this naive formula as a way, the formulas as in like things like number of spams divided by n, and similarly for the previous slide. Where was the previous slide? Oops, not that one. I shouldn't have done that. Okay, doesn't matter. In the previous slide, there is also probability of word 1 is equal to appearing or not appearing given y is equal to spam. The same thing. It's basically, for example, estimate for this is the number of times word 1 appears and spam divided by number of spams. That's what this is. And this is also you can get by maximum likelihood estimation. So hopefully this is an example where this is a second example. So if you are not very familiar with maximum likelihood estimation, which is fine, since I've just introduced it in this class and previous class, this is just a way to think about a model and then estimate the parameters in a natural way. Okay, instead of like pulling squared loss out of directly, like designing a squared loss directly. It's basically, but if you assume some sort of Gaussian assumption on the data, then the squared loss directly comes because you can see that Gaussian density has this e to the power minus squared thing over there. So if you take a log of it, you essentially get the squared loss directly. Okay, so that's what we saw last time, and this time I'm just giving an example for naive-based classification. Okay. Any questions about this part?
So the crux of this, like whenever you do MLE, is that our distribution assumption should be proper, right? If it goes wrong, then
yeah. So we're making distributional assumptions here in the sense that so his question was if we make the wrong distributional assumption, which is like if these are not Bernoulli, if they are something else, then we would get some estimate, but that model would not be reflective of the true data. If the true data came from Gaussians, let's say in reality, so here we cannot really say much because everything is Bernoulli binary, so it's all Bernoulli. But if the true data was not Gaussian, maybe it's let's say here is an example. Let's say the true data is actually, let's say it's one dimensional, and the data looks like this. Okay, and what if I wanted to fit a Gaussian to this? Maybe some sort of a Gaussian like this. Okay, so from this I got data. So I drew histogram. Maybe it looked like this. Okay, so given this histogram, we can see, okay, we eyeball this, okay, it looks somewhat Gaussian, maybe it is Gaussian, so you fit a Gaussian, so you get some mean and variance, okay, mu hat and theta hat using MLE. But if the true data is like this, then there's going to be mismatched, right? So this has nothing to do with, this true data distribution function is not like that. So there's going to be a mismatch, okay. And in fact, we'll see how to look at richer models in the next class after the exam, which are called Gaussian mixture models. Okay, a mixture of two Gaussians, in the sense that there are two Gaussians overlapping with each other. Okay, and you can estimate the means and variances of that mixed Gaussian using same idea, maximum likelihood estimation, but there's going to be some nuance there because it's a messy two peaked distribution rather than a nice single peak distribution. Okay. Any other question about MLE? Okay. So let's actually go to, so the reason why I kind of revisited MLE today is Bootstrap, as we will see, is a general way to estimate uncertainty for both models and predictions. Okay. But so before I get to the uses of Bootstrap, let me tell you what Bootstrap itself is. Okay. So Bootstrap is a procedure. So I will tell you what the three steps of the procedure are, 3 odd steps. So okay, so in Bootstrap you start with some data. Okay, it's all so there is no, I mean, at least in this treatment we are not going to think of some distribution and all that. So there's some data. Okay, I'm going to use capital Z with tags at the top left and bottom right to represent that this is the data, which means that this could be x1 y1, x2 y2, all the way to xn yn. So these many observations, right? This pairs of observations. Sorry, this. Okay. So Bootstrap is as follows. What we do is from this data we're going to create multiple copies of data sets. Okay, which I'm going to call Z star 1, Z star 2, Z star B. Okay, there are going to be B copies of this data set, and how am I going to create it? I'm going to sample each row with replacement. Okay, there are many variations that you can have, but let's look at one variation where, given the original data, I'm going to sample some number of rows with replacement. Let's say my original data has capital N number of observations. Let's say capital N is 100. Then I'm going to do 100 samples with replacement, from 100 samples with replacement from the original data to get Z star 1. and then again 100 samples with replacement to get z star 2, and again repeat this whole thing for b number of times. Maybe b is 30 times. Okay, I create 30 copies of my data from my original data, okay, using this procedure, and then with each data set I'm going to fit a model. Okay, let's I'm going to use f hat star 1 to represent that model, f hat star 2 to represent that model, all the way to f hat star b to represent that model. Okay.
So when you're picking up the samples, so does that sample contain all the features or some features and some rows?
It contains all the features, but potentially some rows, because I'm sampling the rows. It contains all the features. If P is 5 dimension, if there are 5 features, then all 5 features are going to be present in.
So, but the number of rows is equal to the original data set.
Yeah, so so there are several choices I'm making. First of all, that here I'm going to pick n observations, n observations, n observations. I'm going to sample with replacement, n observations. I'll keep the features the same. Yeah, I guess those are the choices I'm making. Yeah, but you can have variations. Okay. And they all probably are variants of Bootstrap. So, and then with each data, then I just use fit a model. Okay, so model fitting given training data, you know how to do it, right? So once you fit the model, fit B, these capital B number of models. Okay. Then first thing you can do is what's your prediction? Let's say it's a regression problem. Then your prediction is going to be just an average of these models. Okay, so it's just going to be sum over, so 1 by b little b is equal to 1 to capital B of f hat star little b of some x test point. Okay, so this is your prediction. Okay, it's like some sort of an ensampling. I have too many models created from replicas of my data, but these replicas are not exactly are sampled replicas. Okay. Second thing I can do is estimate ERR by just generalization error. Okay, I can estimate generalization error using Bootstrap. Okay, and how do I do that? I fit these models using this data, right? So in z star 1, maybe my original data n, let's say n is 100. Okay, I sampled 100 observations, right? Maybe it turns out that out of the original 100 observations, maybe 20 of them did not feature in my z star 1. Okay, this is z star 1, because I was sampling with replacement, but I never touched those rows. They were never sampled. Turns out, okay, in that sampling run. Then those 20 observations are like the held out data for this model, right? So I can compute the performance of this model f hat star 1 on that held out data. So I'm just saying that if when you created the first data set, you might have missed some rows. Just use those rows as your held out data for evaluating this model. And similarly, you do that for every model. Okay, and then you average the performance. Average the held out errors across all these capital B in, let's say, in all these 30 models, and that's going to be your estimation of error if the model, given the model family, for example, is linear or something like that. Okay, so just average held out data, average I guess performance on held out data for each f hat. Performance on held out data, just average it. Okay, that's an estimate of ERR. So this is I guess a direct way to estimate ERR. It has its own, I guess, pros and cons, but this is one way to estimate.
Can you explain once again? Like, suppose you said that there are 20 observations which
Yeah.
never gets picked when you did sampling for 30 times.
No, it never get picked when I sample the first data. And those 20 observations would be used to estimate the performance of f hat star 1. Okay. Maybe for when I sampled with replacement for z star 2, maybe there were 5 observations which could be different from the first one that were not sampled. Okay, that did not feature in z star 2. Then those 5 observations would be used to evaluate f hat star 2. It's like data that was not used to build that model is being used to evaluate that model. That's all. Any questions?
One question. For every time that f is like, if I use linear regression, every f is I'm performing only linear regression. I'm not using one step linear regression, other step lasso or something like that.
No, it's the same model family.
Same model family. Okay.
Yeah. So you could. So this is a way to estimate error, right? Then you could change. Okay, what if I used? Let's say if you compute this using Bootstrap, you create the Bootstrap samples. Now you can ask, okay, if I use only 5 features, I get some estimated error. If I use all the 10, all the 20 features, maybe I get some other estimated error. You can compare them and pick the one which has the lower estimated ERR. Okay, it's like cross-validation. So you can also get confidence intervals, equivalent confidence intervals. These are called confidence bands. Okay. Around estimates. Okay. For example, if you have estimates as in beta hat is an estimate, right? So you don't have a single beta hat because I had 30 models. So I'll have 30 different beta hats. Then you can, per coordinate, I have 30 numbers. I can look at its mean and I can look at its standard deviation. Okay. And I can also estimate confidence band around a test point. Okay. So if I have, so I can do f hat star 1 x test all the way to f hat star, I guess, 30 x test. So I'll have 30 numbers, right? This is like 1 cross 30. So 30 numbers, right? Because I have 30 models. Then I can just sort and pick the, I can take the average, of course, that's my prediction. But I can also get a band around it. Like, for example, if I want a 95% confidence band around it, then I have to drop 2.5% on this side and 2.5% on this side. Okay. So I sort these numbers and pick the first and the 19th number, for example, as my band around my prediction. My prediction could be just the average of these numbers. That's what I just showed you in the previous slide. And it need not be just average. It could be like 10th observation once I sort this, right? It could be like some sort of a median prediction. And my band around it could be drop few predictions at the bottom and the top. Okay. So that will give me a confidence band. 30 is too small. Like, let's say if you had 200 observations, okay, 200 Bootstrap versions, then you would have 200 observations, 200 numbers here. Then to get a 95% confidence band, you would drop 2.5% on the left side, 2.5% on the right side. 2.5 corresponds to, since I have 200 Bootstrap examples, corresponds to 5 observations on the left side and 5 observations on the right side. So I can drop 5 and 5, pick the remaining 190, and whichever, what is the top and bottom of these two would be my confidence bands, lower and upper values. Okay. Yeah.
So they'll be different for all the f-hats, right? All the models.
So this is for a given observation, my prediction, and a confidence band around it. So I'm using all the f-hats, all f-hats predictions, which will be 200 in number if I had 200 Bootstrap samples, to estimate 95% confidence band around a given test point, which is x test.
How does this differ from, like, when we calculate the confidence interval, we use only like variance of the data and all that, right?
That's a assumption based thing. So you might have seen actually for linear regression, if you assume y is equal to beta transpose x plus epsilon, where epsilon is normal with mean 0 and variance sigma square, then you estimate. So these are parameters of this model. Okay, you can assume x to be random or not random, and so y is going to be normally distributed with some mean and variance. You can estimate variance. So what you would estimate is this beta and the sigma. Okay, based on that, you can know what the beta hat would be a function of the data. So it's also a random variable if data is random. So you can, since it's a random variable, you can have confidence bands because it will have a distribution function. You can have a band, confidence band around it. And in this example, the prediction is going to be normally distributed, and so therefore the band is going to be something like a normal distribution. So normal distribution's variance will give you some information about the band. Okay. We have not gone into details of that, so this is just a very on-the-fly explanation. Any other questions? Okay, so let's take a 9-minute break and resume at 7:35.
It's not gonna pop up, so I know it's already.
So okay, let's resume. So I'm just gonna list a couple of things that if I have time I'll cover today, which is, I think in its order of priority, which is first one is PCA and ridge regression. I kind of missed this, I think in the second or third lecture. So if we have time, we'll get here. Okay. Second thing is, y beta hat is x transpose x inverse x transpose y. Okay. In the sense, the calculus involved, it's kind of laborious and mechanical, but if needed and if time permits, I will go through it. And if there are other things, I'll add in. So what I'm going to do for the next, I guess, few minutes is go through the topics, go through the first 6 chapters, just to kind of revisit and see if you have any questions about any part that you want me to repeat. Okay. So the first chapter was about, I guess, first lecture was about K and N and linear model without the notion of, I guess, a statistical background. So so for example, in the first lecture there was this question about what should K be, okay, and one example choice was K is equal to 1 would give you 0 training error, right? K is equal to 1 gives 0 training error. Is everybody able to see why this is the case? I'm just going to pick a few, I guess, key points from each of the lecture and just double check that you guys know what it is. Okay, so
This is for only regression, right? Not for classification.
it doesn't matter here.
No, but if we do a classification, the nearest neighbor, so I go to the nearest one. Regression means I check with the same point and that's my average, right?
Yeah, even with classification, K is equal to 1 means the nearest point to me is myself. Okay. In the sense, whether it's classification or regression, on my training data, the nearest point to me is myself, right? So the point I have. So whatever the label I have is what I'm going to predict. So therefore for my training data, I'll predict 0. I mean, always predict the correct thing. So therefore my training error is going to be 0.
how it works, like when I use like k equal to 2, I check.
Then look at the 2 nearest neighbors.
So the first neighbor.
Yeah.
If you're looking at just one neighbor, then you basically your error will be 0.
Any questions about this? Okay.
The diagram, sir, like we did in the first lecture, suppose you're looking at only the first, like nearest neighbor.
Yeah.
Suppose your nearest neighbor stays red, then.
Yeah. So for example, if this is the point which is red, okay, and there could be blue around, maybe here's red, and maybe another blue here. So the one nearest neighbor of this would be just training in the training data. So I'm asking. So these are the 4 points in my training data. Let's say in the 2D space, x1 and x2. So on the training data, I want to make training error. I want to estimate training errors, which means that on the 4 training points, I'm going to estimate what my prediction is. If I'm looking at k nearest neighbor, it's a lazy classifier, or let's say in this case, it's a lazy classifier. So I'll pick the first training point, which is let's say this is the first training point. Look at its nearest neighbors. Okay, one nearest neighbor for this point is the point itself, and it's going to classify it as red. And in the training data, it is red, so it's therefore the error on that point is 0. Similarly, I move around, I get 0 training error. Is that fine? Yeah, and we also, I guess, in the first lecture we didn't really spend too much time on this, but for example, linear model would give us a linear decision boundary. And decision boundary is the bunch of points in the input space where I don't know which class I belong to. Okay. Whereas KNN decision boundary could be arbitrary. It could be some patch like this, some other patch like this. This could be red, red. This could be blue here. It could be some other small patch of red. Okay, it could be anything. It could be also wiggly line. Or k is equal to n. We figured out what the KNN's decision boundary is going to be. What is the decision boundary going to be for k is equal to n? So when k is equal to n, I will predict the same class for everything. Maybe always red, always blue. So you'll not see a decision boundary. Okay, maybe the decision boundary is at infinity or something. Okay. Okay. So in lecture 2, one of the key concepts was the idea of a regression function, which was the conditional expectation of y given x is equal to x, or conditional expectation of y given x, and how we thought, okay, KNN is going to approximate this, and the linear model approximates this as beta transpose, I guess little x. Okay, so this is what we kind of discussed in this part. Okay, if KNN can approximate this conditional expectation of y given x, and we figured out that conditional expectation of y given x is the best one if the loss function is squared loss, and we're looking at expected square prediction error, right? But it's not always, although it's best one in I guess theory, it's not the best one in practice, and that's because of curves of dimensionality. Okay. So what was the curves of dimensionality? It's basically how much, your neighborhood size kind of changes. If you want to keep the same neighborhood size or proportion as you increase in dimension, you're looking at neighbors which are very, very far away. Okay. Or an alternate view is that if you want to keep the same proportion of neighbors, then you are looking at neighbors points which are very far away. or if you fix a fraction of the neighbors, like if I only look at 20 neighbors, then as you increase in dimension, they're going to be, what is it? So what's the right way to say this? There's going to be extremely small, so you change the neighborhood size from a large space to a small area. Okay. Okay. So I guess I didn't say that really well. All I'm saying is, as you increase the dimension, say, so if I want to make the neighborhood size the same, so for example 10%, okay, of the neighbor, 10% of the full input space, let's say it's all bounded, between all features are evaluating between 0 to 1. If I want to keep the same neighborhood to kind of estimate what my label is or what my prediction is, then the neighbors in this 10% region will have feature values which are wildly varying as I increase the dimension. So for example, in one dimension, maybe the side length is 1/2. So I'm looking at plus or minus 1/2 from this particular feature. In 2 dimensions, I'm going to look at 1/4 plus or minus 1/4 of each feature, and similarly in okay, sorry, not 1/4 but 1/4 to the power 1/2. Actually, that's not correct. So side length is going to be 1/10 here, and the side length here is going to be 1/10 to the power 1/2. Okay, it's just product of 1/10 to the power 1/2 times 1/10 to the power 1/2 is 1/10. That's what I want, a 10% volume, right? So similarly, you can see that in higher dimensions, you'll see that it's a number which is like almost 1/10 to the power 1/100 is a number which is like 0.99. So I'm just saying that each feature, you're essentially looking at neighbors whose values in that feature. For example, if you're looking at one feature is about income, so it's let's say the average income is 50,000. You're looking at 50,000 plus or minus 50,000 in that dimension, which is like a huge variation. Okay, to keep the same neighborhood size. That's the curse of dimensionality. Or equivalently, you can say if I only want to consider 20 neighbors, my neighborhood size is shrunk, so which means I'm more unstable. Okay, I'm not going to make good predictions. Okay. And in lecture 2 itself, there was this relation between residual sum of squares. Okay, before that, this one point. This next point was about classification. So Bayes classifier. Bayes classifier is the best classifier that you can have given the joint distribution between the outcome, which is going to be qualitative, and the input variable. Okay, so given P of Gx, the joint distribution between G and X, the Bayes classifier would be the best classifier, which minimizes the 0-1 loss. Okay, remember the loss function was written as a matrix where the diagonal elements were 0 and off diagonal elements were non-zero. And Bayes classifier, think of it as like pluses and minuses. The Bayes classifier would give a decision boundary. It's called the Bayes decision boundary. Okay, and we saw how to get the Bayes classifier and what the Bayes decision boundary means, what a decision boundary means. Okay, that we saw in the previous lecture as well. And there were some variations of KNN and linear regression that we saw. For example, for KNN, you can have, instead of this sharp cutoff of k neighbors and nothing else, you could have weights where the more closer the training data point is to the current test point, the higher the weight you give. So if you're trying to make a prediction at a test point, you look at all your training data, look at the closest ones, whatever predictions they are making, upweigh them, like maybe put a weight of 0.9, 0.8, 0.7, test training data points which are very far away, their predictions you give them very low weights. Okay, it's basically an averaging of all the training points, but you give more weight to the points which are close to you. Okay, this is like a kernelized version of KNN. Okay, we saw this example, and also there was, so in the notes at least there is this thought, there is this points like, what if you have interaction terms, what does interaction term mean, and when does the data not have a, when can you not use that formula that x transpose x inverse when the inverse doesn't exist, and why doesn't inverse exist, at least one reason for that. Okay, so there were those considerations. There was also, so there was also this I guess a matrix notation for residual sum of squares, which was y vector minus x data times this transpose y minus x data transpose b. So this, so transpose times y minus x beta. So what is this? This is actually a n cross 1 dimensional vector, and this is a 1 cross n dimensional vector. If you put a 1 by n in the front, this is the same as sum over 1 by n yi minus xi transpose beta square. Okay, so you should not get confused between these. I mean, this is just a, this is the scoring function for any model, and you are trying to find the best model, beta. Okay. Okay, next, lecture 3, we briefly discussed what is called bias variance trade-off. And it makes sense even for linear models because, for example, I think even today, or at least as recent as a couple of years ago, especially in advertising, people were literally building large-scale linear models. Okay, where the number of features is in the millions. So there, you really want to, if you have million features, like the example that we were talking about when we were talking about cross-validation, you would have spurious correlation. So you really want to drop, even a million feature linear model is highly I guess high variance, has high variance. So you want to kind of further bias the model. So that's why we were looking at subset selection and ridge regression and all that. And that's why bias variance topic was even introduced even in this place where we are just talking about linear models. But but as a rule of thumb, you would, at least it looks like as of today, you should start with a high variance model and then prune, regularize, and delete things and so on. So that's to restrict the capacity of the model, restrict the model. So start with something more complex and then drop it, prune it, reduce it so that you have less overfitting. Okay, rather than start with a underfitting model like a line or something and then add complications on top of it. Okay. So we saw like so this topic also comes up I think a couple of lectures later in lecture 5, but we saw for KNN how for example bias, I think the variance term is proportional to 1 by k. Okay, so when k is large, there is very low variance, and we saw that, right? K is equal to n, there is no variance, it's literally flat, it's always predicting the same thing. Okay, that's heavily biased and low variance model. Okay. Variance of the classifier was proportional to 1 by k. Okay. So actually there was a part that we did not discuss, which is a linear regression with these things like hypothesis tests and z-scores in that section. So yeah, I don't think I should go into the details now because I don't have time. So but okay, so what is the sampling properties? sampling properties of beta hat, the key thing that you should know is what are the assumptions being made. So we are actually assuming that y is beta transpose x plus some epsilon, where epsilon is normally distributed with mean 0 and variance sigma square. Okay, and assume that x is not random. Okay, and if you make multiple observations, you get data from this. One observation has nothing to do with the other, in the sense they are independent. Okay, some independence. Under these assumptions, then you can kind of estimate beta hat. Okay, in the sense of beta hat would be essentially if you know sigma hat. So if you know the sigma, then beta hat is actually normally distributed. Okay. Yeah. So beta hat minus the true beta divided by some scaling is actually, okay, let's say proportional. So that random variable is called z score. Whatever. This is normally distributed. Okay. So all I'm saying is under the square box assumptions, you can have an estimate beta hat, which is the usual, x transpose x inverse beta, x transpose x transpose y. So that thing is actually essentially normally distributed, as in that minus beta divided by, I think, sigma. I said sigma is known. Let's say sigma is known. If it's known, then this thing is normally distributed, but it also depends on, I think, let's say x's are uncorrelated with each other, then this is normally distributed. Okay. So if it's normally distributed, you can test for things. For example, if you think that in the true model beta is 0, then you can ask how, what the z score is. That will be beta hat divided by some sigma. Sigma is known, and you see that number is large in but in your null hypothesis, you are assuming beta is 0 for, let's say, the ith coordinate. Let's say this is the ith coordinate. Then you can say, oh, I observed something different. I'm assuming normal with mean 0. If it's really large, then I need to reject the null that it is 0. Okay, that's roughly the idea of a null hypothesis testing for beta coefficients under these assumptions. I went over this very quickly, but is the high level idea clear? It turns out that under those assumptions, this beta hat, each coordinate is normally distributed with some correction, with minus something divided by something. And if it's normally distributed, you observe some number beta hat maybe 10 or something, and your null hypothesis is 0, then the probability of under the null of observing some large quantity is really low. The p-value is really low, which means that, but then you observed it, therefore you should reject the null. Okay, that's roughly the idea. Any question? Fine. Okay, so and as I was saying, in practical applications, even for linear models, can be high variance. So you want to, and we went through a sequence of ways to add bias, which are subset, selection, ridge, and lasso, right? And with subset selection is where we came across, how should we run a cross-validation loop? So how many subsets were there for each subset, or each subset size choice? We need to figure out what is the right subset choice. Okay, there are various actually greedy ways to do so as well, but we did not discuss how to figure out the best subset. We said, okay, if there are 20 subsets, then we can just evaluate each one of them and figure out the EPE, and hopefully whichever one has the lowest EPE, that's my right subset. Okay. There's another thing. Okay, that reminds me. In cross-validation, k-fold cross-validation, if you have too many choices, then it's not clear if the number of choices also influences the quality of your EPE. I mean, quality of your estimation. Okay. So this is something we can discuss later. Okay. So in that lecture, basically, we saw subset selection and cross-validation. Okay. Any questions about this part? I mean, if anything is confusing, I can repeat it. We have about half an hour, so. Okay, so in lecture 4, we looked at ridge and lasso. We basically looked at geometric point of view, like basically those squares for lasso with some elliptical contour lines for the loss function and where they intersect, kind of motivating that maybe they are approximating or kind of mimicking the subset selection procedure. Okay, and ridge also somehow the geometric picture was you're biasing towards all the weights being close to 0, but you cannot set all the weights close to 0, then loss function would be high. If you set loss functions to be 0, then the weights could be large all over the place. So you're balancing those two. So you're balancing two terms, right? For example, in ridge, you're doing sum over yi minus xi transpose beta square plus sum over j beta j square. Maybe you can put 1 by n here plus lambda. So this was the ridge choice. Okay, what does lambda correspond to? If lambda is really small, so if lambda is really small, then you're looking at picking any model from here. Okay, picking a model from here for some lambda. Okay, lambda, let's say small. If lambda is large, then you're picking a model from a smaller set. Okay, this would be lambda large. Okay, so you're picking, if you're using large lambda, then you're really biasing your model. You want almost all the coefficients to be strongly like 0, ideally. Of course, it has to be balanced with the loss function. So the loss part, which is the first term. Okay, and the second term is saying put the beta as close to 0 as possible, right? So we saw this geometric view, and we also, I think this and probably the subsequent lecture, we saw the likelihood view. So basically, if you have a normal distribution prior on the betas, and your likelihood of y given the beta is also normally distributed, then the normal distribution's exponent, normal distribution exponent, if you take a log of the likelihood, the exponents are basically squares, so they basically turn out to be this part and this part. Okay, so this actually, is this a part of your assignment? No. Did you have to derive, so did you have to relate lambda to the parameters of your normal distribution assumptions? You haven't? Okay, maybe it's part of the third assignment, so it's out anyway. So all I'm saying is we looked at the likelihood view, where if you have a normal distribution prior on beta, normal distribution prior on the likelihood, probability of y given beta and y given beta and x, then dot likelihood times prior, if you take the log, it turns out to be this term and this term. Okay, that's the, I guess, likelihood point of view of why we are balancing these two objectives, a loss function and a squared sum of squares type of thing with the lambda in the front, right? So we skipped interpreting this ridge regression using SVD. I want to get to that hopefully in a few minutes. So any questions about this part? And in terms of computation, it turns out that actually for ridge regression, the beta hat ridge also has a closed form formula. It's basically x transpose x plus lambda identity. Identity is the matrix where all entries are 0 except for the diagonal entries are all 1s. Okay, the whole inverse x transpose y. Okay, I mean the formula itself doesn't matter, but you can see that, why did I get a lambda times identity? It's because this guy here, if you remember, I said RSS beta, so this was something like this, right? So it's lambda times, so this was the ridge regression objective, right? This is nothing but y minus x transpose beta transpose y minus, sorry, this is not, let's say we have data. Okay, this is the data. So I'm putting tags at the top, please be careful. This tag at the top, this one. So that's data plus lambda beta transpose identity beta. Okay, so beta transpose identity beta are norm of beta 2 square or the sum of the beta j squares is all the same thing. Now if you just expand the square and put terms together, you will see that there is going to be a beta transpose something beta. Okay. So it's like y transpose minus beta transpose x. Y minus x beta and beta transpose. So oh, I'm missing something. Oh, this was not correct, right? This transpose was not there. Oops. So you can see that this term here is beta transpose x beta plus lambda beta transpose identity beta. So that kind of gives you a hint that that x transpose x plus lambda times I would be the factor there. Okay, this factor here, and these two terms here. There's an x transpose x, beta transpose x transpose x, and just a lambda times identity. Okay, with the pre-multiplier and the post-multiplier being beta transpose and beta respectively. Okay. Anyway, so this was just I mean I didn't really do anything. I just wrote just expanded the squares. Okay. So anyway, all I wanted to say was ridge regression has a closed form expression. Lasso does not have. So, but in general, I would suggest that the common way to think about any of these models, except things like decision trees and so on that we'll see later, is that as long as the objective is something nice like squared loss and so on, or hinge loss or whatever, we'll see loss functions later, few loss functions later. Nice in the sense as long as it's differentiable. Okay, 0-1 loss is not. 0-1 loss looks like a step function. Okay. Our indicator functions are going to be step functions like this. By step function I mean it's like x versus y is going to be have discontinuity. So as long as the loss function is like a squared loss like this guy, this is a nice objective. And if your model is bunch of numbers, continuous basically, then you can just do gradient descent. Okay. You can't do gradient descent directly on decision tree type of models. There's something else that you can do, but here you can just do gradient descent, these types of models, ridge regression. So you don't have to think of closed form formula for the original vanilla ordinary squares, for ridge regression, for lasso, for logistic regression, for LDA, any maximum likelihood estimation problem. As long as the objective is nice, likelihood function is nice, and the parameters are nice real numbers, then you can just do gradient descent. Okay, and we saw an example of gradient descent script, right, few lectures ago. Okay, so any questions about ridge, lasso, and subset selection? So after that we said, okay, let's try to finish this chapter about this sequence about linear models. So we looked at how to use regression for classification. Okay, and the cool part here is actually that the formula remains the same. So beta hat is equal to x transpose x inverse x transpose y. But the nice thing about this is that we said, first of all, if you have a qualitative variable, let's say it's three classes, then you'll have a y to be one hot encoded. So it's going to be n cross 3. Okay, So so you'll have the first column representing whether the first class is present or not, second column representing whether the second class is there or not, and the third column representing whether the third class is there or not. Okay, and only one of them, for example, could be 1. Okay, so for this, you can think of this whole thing as some matrix A. Okay, some linear transformation, because the whole thing is transforming this n cross 3-dimensional vector to okay. So this thing is P cross P. This is P cross N. This guy. This thing is P cross P. Anyway, so there's a mapping from n cross 3, those n cross 3 matrix. There's a matrix A, which is some dimensions, I guess P cross N, to get me a P cross 3 matrix. Okay, that's my linear model for regression. Okay, and the way to think about it is the following. So what is it? It's as good as saying, okay, let me look at my data, which is the x data, script x, so the x with the tag at the top, and I'm going to pick only one column of my output variable, and I'm just going to do linear regression on that one column. Okay, if I just do linear regression on the one column, on the first column, I'll get some coefficients, right? I'm just predicting whether class cat is present or not. Okay, so I'll get some coefficient, right? So that those coefficients are going to be this first column of this beta matrix. Okay, so and I can do another regression with the second column as my output variable. Just do linear regression with the second column as the output and my usual data as the input. I'll get another bunch of coefficients, p coefficients. That's going to be my second column of my beta hat matrix. Okay, so all I'm trying to say is that this regression for classification has multiple outputs. In this example, 3 outputs. Okay, having 3 outputs for a linear regression problem is the same as me doing 3 independent regressions. Not independent because I'm using the same data, but it's the same as doing 3 regression problems separately. Okay, there is no complication. It's like I can estimate the first bunch of coefficients first, and then the second coefficients second, and third coefficients third. And that's because you can see that if I have a matrix, I'm just doing a linear transformation. It's as good as saying I'm going to apply A on the first column, A on the second column, A on the third column, and I get 3 p-dimensional vectors. Okay, it's just a way to think about it. I know it's probably in real time it's difficult, but for those who want to think more about this, this is a way to think about regression for classification. This is a way to think about regression. So what is meant by previously we have been talking about regression as just being estimating p numbers, right? Here we are estimating p numbers times 3, and I'm just saying that that's the same as 3 separate regressions. Okay, and then we looked at LDA versus logistic regression. Okay, and the key point was that LDA makes distributional assumptions. It assumes that the conditional probability of x, conditional probability of x given y, so given the label, is normally distributed. Okay, so there are some bunch of assumptions that go with LDA. So for example, normality is a big one. Under normality, it turns out that the linear log odds ratio, which is the ratio log of the probability of class 1 divided by probability of class 2 given x is equal to x for both sides, the log odds ratio is linear. Okay, that's the consequence of making that normality assumption. Okay, so assume something is normal. What is normal? Given the class, the probability of x is equal to taking any little x value is normally distributed. Under that assumption, log odds ratio is linear. Okay, that's why it's linear discriminant analysis. In logistic regression, we kind of skip the normality assumption and directly say, okay, what if I directly assume that the log odds ratio, I don't know what the distribution of x given class is, but what if the log odds ratio directly is linear? Okay, that's the assumption in logistic regression. Okay, if you make
logistic regression, it can only handle like binary decisions, right? You can't give it like 3 or more classes.
You can. So there's multi-class logistic regression, and we saw In fact, if you think of neural networks or even the zip code data, right, it has multiple digits, right? It's not just 2 digits that you analyze. So if you have multiple digits and you want to apply logistic regression, you can apply. We saw a loss function which we call the cross-entropy loss function. Okay, do you want me to write it? So we saw a loss function which is called the cross-entropy loss function. So let's say y, for a particular observation is 1 hot encoded. So it's like let's say there are 10 digits, 0 to 9. Okay, so this is 1 cross 10. Okay, 1 row and 10 columns. So let's say this is my observation. This is the digit outcome variable, and the digit itself, the features are like 256 dimensional that we saw in the assignment, right? Then the cross entropy loss for this observation. Okay, loss is generally a sum over loss per observation anyway. We saw that in residual sum of squares. It's a loss per first observation, which is y1 minus x beta transpose x the whole square, right? Similarly, second observation y2 minus beta transpose x2 the whole square, and so on. So it's per observation anyway. So for the ith observation is sum over I guess ij. So j is this index. Okay, j is equal to 1 to p. Let's say there are p classes, or actually let's make it k classes. Okay, times the probability that I'm predicting for the kth class, which is actually the probability that I'm predicting for the kth class is e to the power beta j. Okay, I don't want to use j. Let's put L transpose x divided by 1 plus sum over L is equal to 1 to, okay, I don't want to use L there. Little k is equal to 1 to k minus 1 e to the power beta transpose little k x. Okay, so this is called the cross entropy loss. This is the logistic regression loss. Okay, if you think of two classes, then y could be 2 dimensional, and you just have a ratio like this. Okay, k is equal to 2 here. Okay, so basically this is the loss function. You pick any k is equal to 2, 3, 4, 5. This is a loss for the ith observation. So if the ith observation is picking the ith observation, the true class was let's say dog. So maybe this corresponds to dog or the digit 7. Let's say this is the digit 7. Then the 7th digit. Okay. Then for this observation, the loss for my current parameters, the parameters are going to be this beta L with L is equal to 1 to k minus 1. Remember, these were the parameters in multi-class logistic regression or logistic regression. The loss is going to be pick the 7th probability, which is going to be beta subscript 7 transpose x. Okay, e to the power beta subscript 7 to the transpose x divided by that normalization factor. Okay, that's it. So it's basically saying logistic regression is just saying for each observation what was the true thing in the training data for that observation. That true class, pick the term corresponding to the true class. Okay, because this this is going to be one only for one of the entries. Okay, so you will see cross entropy loss in several locations, especially in neural networks. So it's good to familiarize yourself here. And if you're confused, just ask me right after the class. Okay, further explanation for this. And okay, now I have lost time. So and then today we saw basically cross validation and Bootstrap for model selection. It's lecture 6 and assessment. Okay, and especially Bootstrap, uses of Bootstrap to estimate these things called confidence bands. Okay, so create multiple Bootstrap samples, build your model, and once you build your model, for example, if you have a prediction, you want a band around it, make the prediction with each of the models of each of the Bootstrap samples you have, let's say 200 of them, and if you want a 95% confidence interval, get those 200 numbers, drop the first first 5 numbers and the last 5 numbers, sort them and drop the first 5 and the last 5. Then you'll get the confidence band. The first number on left, first and the last number on the right. Those two will be the confidence band numbers. Okay. Any questions so far? Yes.
Yeah, just in general for the test, where you can bring in a cheat sheet. Is that right?
Oh yeah, so the syllabus page has this information. I think you can bring in a cheat sheet. I'm not sure. Let's see. Yeah, so one cheat sheet is it has to be handwritten, I think. Yeah. So.
How about do we get equations or anything?
What is it?
Do you ask any mathematical equations or anything in the test?
No, but try to see the sample exam questions at the end of each of the notes. Okay. Try not to. So if you haven't seen the Elements of Statistical Learning book now, don't try to read it in the next 1 week, because it's try to follow one book. So at the minimum, my advice is definitely follow Introduction to Statistical Learning. If you can understand each of the chapters, that's really good. You will be a really good data scientist essentially if you can understand each of the chapter well for that book as well. If you are more if you want more challenging text, then that's Elements of Statistical Learning is a good point. Yeah. So actually I wanted to do regression using PCA. So let's see. Sorry, ridge regression using PCA. Sure.
Can you explain why does Bootstrap, how does bootstrapping decrease the variance of the model?
Did I say that? So your question is, how does bootstrapping decrease the variance of a model? Oh, variance. I think you're talking about something called bagging, okay? And we'll get to bagging, 2 lectures from now. So right now I just illustrated what the bootstrap procedure is for 2 things. One is to estimate the generalization performance, like how will this model family, let's say linear models, perform in the future, okay? And second thing was how to estimate confidence interval, credible intervals. Sorry, confidence bands, okay? So those are 2 things, 2 applications. So this notion of Bootstrap reducing the variance of modeling in terms of Bias-Variance Tradeoff, the correct word is called Bootstrap aggregation, okay, or bagging, and we'll see bagging 2 lectures from now, okay. So we'll revisit that point. Okay. Actually, given that I don't have time for interpreting ridge regression using SVD, I'll skip it. But it's in the notes. Have a look at it. And if people want to discuss it, I'm available after this. Any questions in the next few minutes about the exam or what we have covered so far? So we have been looking at a very particular class, linear family of both classification and regression. What will happen next is after the exam we'll look at again MLE a little bit, because it's a nice. It turns out that many problems are not canned into least squares loss and so on. Okay, so we'll look at something called like the Gaussian mixture model I was talking about. If it has 2 peaks, then how to estimate the parameters of those? It's not even a supervised learning problem, but how to estimate the parameters of such a thing? If I draw the histogram and estimate the parameters of such a thing, we'll look at that. We'll look at something called sampling, and we saw sampling with replacement here in Bootstrap. But how do we sample? Okay, and there is a thing called Gibbs sampling that you might have heard of. We'll look at Gibbs sampling. So that's the immediate lecture. But then after that, for a few lectures, 2-3 lectures, we're going to look at nonlinear regression and classification models. Okay, so that includes the things that you're familiar with: random forests, support vector machines. Because you spend so much time on linear models, you should be fine with all the the diagnosing and the basic setup of a regression or a classification setup. The only thing will change is the definition of the model. Okay, the SVM model will look slightly different. Random forest model will look slightly different. But all the other considerations, cross validation, everything should be well grounded from this part of the course. Okay, and then after we look at few nonlinear models, popular nonlinear models. The last stretch would be looking at unsupervised learning, and that's where we'll kind of visit PCA and variations like spectral clustering and clustering methods and so on, association rules. You might have seen some of these, but we will revisit them from a statistical perspective, understand why and what's happening. Okay, and if time permits, we'll get to what's called time series method.